say recording, so we'll start recording it. Wrong class for this. If we think through kind of goals of organic chemistry, some goals are explain how things work. So it's getting into mechanistic detail. And ideally, we would reach a point where we understand the mechanistic detail for everything. Okay? But there's lots of people that don't care how it works. They care that it works. If you talk to a contractor or a builder and ask them, how does a screw hold two pieces of metal together? What are they going to say?
I don't know.
Okay? They don't care how the screw does it. They just care that it does it. So depending on your focus, on what you're trying to do.
Well, that's kind of halfway my point is, then why are we learning all this if it doesn't really matter in the end?
Some doesn't matter, some does. It all depends on where you are going with that content. So to me, what we're talking about with organic chemistry, I don't care that you know, because that's not really relevant. To a significantly lesser I don't care. I don't care necessarily how, or that you know how either. What I care about is that you're putting logical arguments together to create a flow of how you would problem solve. You're just problem solving in organic chemistry. Okay? When you go out into the real world, are you going to be doing organic chemistry? Probably not. So what we talked about within the class isn't relevant, but the structure on how you think about an approach and break down a problem is relevant.
Well, the reason why that's curious, so because I know I'm the only chemistry major in here, but doesn't that mean organic chemistry directly applies to me?
Nope. There are plenty of organic chemists that hate there's plenty of chemists that hate organic chemistry. Talk to actually the vast majority, interestingly enough, of biochemists. They all think organic chemistry is utterly useless.
But organic chemistry is the basis of all they do.
Don't talk about logic with them. Right? I probably shouldn't have recorded that part. Okay? But yeah, it is the basis, the fundamental behind it. But again, a lot of that comes down to, do they care the how? Sometimes they do, sometimes they don't. It depends on the biochemist. You'll find some that really don't care how, and you'll find some that are very passionate about the how. Because you're studying different aspects through different lenses through that system. Okay? You talk to physical chemists, they look at organic chemistry, oh, bah, you're just making approximations and it's all bullshit anyway. Well, yeah, it is, but to a first order approximation, it works, and it works very, very, very well. Okay? But a physical chemist is going to look much narrower at the molecular orbitals and the electrons, where they all exist, how they're moving around, the individual energetics, that they are so zeroed in on that one step that they can't see the rest. And biochemists are going to make the exact same argument against organic chemists. Oh, you're so concerned about what's happening there that you aren't seeing the larger picture. Yeah, no, absolutely. It's 100% true. And biologists can say the same thing about almost any chemical field. You're looking too small in that you're ignoring the larger picture. So an individual class is trying to build you the skills so that you could translate that problem solving into any scenario. And that's how I've tried to structure the class, is to help with that problem solving ability. How do I break down a question to move through it? The problem solving topic that we're looking at happens to be organic chemistry. And if you're going to become an organic chemist, is that skill useful? Very likely yes. Okay. Is that skill useful for any field? Very likely, yes. Is the content useful for everybody? Hell no, not even remotely. So it's going to come to what's your focus. And right now, what you're trying to look at is try and use your skills that you've picked up through the course to try and figure out what's going on chemically, where the electrons are moving around, which is phenomenal. It's great. You're just beyond the scope of the class, which is why I would say pull your horses back. Right? As far as what we need to talk about in the class, let's shift back to what we need to talk about in the class. Outside of class, yeah, let's throw some shit around and see what happens.
Huh.
While you process. Questions?
I'm going to erase this now, I suppose.
It's up to you.
I mean, if we don't know the answer, I can't possibly know if I'm right or not.
Does that matter?
Kind of. Doesn't it? Isn't it supposed to matter?
Do you know where you're going to be 50 years from now?
No.
Does that matter?
I suppose not, but I mean,
Does that make it a bad thing to think about?
it's supposed to, but you said this is far beyond my scope, meaning that I couldn't possibly get this right.
No, I said it's far beyond the scope of the class. Different explanation. So the class does not need to be looking at that because it could very easily be distracting. Okay. Could you, on your own time, look at something else? Yeah, I will absolutely try and figure it out with you, 100%.
So
I still get former students coming in, I don't understand this. I don't really understand it either. But I'll work with you to see what I see out of it and try and come up with it. Perfectly valid.
So you want me to leave it up?
It's up to you.
Okay, then I will leave it up. I don't feel like dropping it.
Okay, you spent the time. So now we had a hot second. What are the questions?
Question 5 on the carbon mill additions.
I think we're looking at yours. Let's just go ahead and see what happens. Please don't lock up. Okay. Cool. I'm tempted to be really mean right here. Should I go ahead and say what I would say to be really mean,
Yeah.
and then you can decide how mean it actually is?
Yeah.
Okay. We just walked through this in the tutoring center, and by we, the people that were there, saying you were there because you started effectively this vein of question, which means you should be able to walk me through it beginning to end.
I couldn't tell.
Okay. And in fairness, there were at least 2 other people there, so you could start it off and you could be like, pass. Okay. So in starting it off, where do you want to start? Because again, this is something that we could look at with 2 different attempts or 2 different focal points behind it.
Well, I guess the reactant, like, is it we're focusing on the lone pairs or that, like the carbon is like an electrophosphate? Why are we connecting the structure of
Right.
the reagent?
So what I'm hearing in your kind of counter-proposal questions is how should I start? Okay. So the approach is there's 2 ways that we start this. One, you've memorized it, which is fair. You can absolutely run that route. Okay. The other way is we do it the same way we always do it.
Look at the most reactive.
We look for the most reactive chemistry and we start to move from there. Okay. What are your thoughts? What do you want to do?
I guess the most reactive
Okay.
reactant is the lone pairs.
Okay. Is the lone pairs. So when you say it like that, I hear there's 1. Well, there's those. There's those. There's those. There's also those. So I'm a little confused. What do you mean by the lone pairs?
On the oxygen and the reactant.
Okay. So the oxygen, well, all of those are reactants. And I put lone pairs on oxygens. So,
The carbon.
okay. So cool. We want to push the carbonyl oxygen. Does anyone want to dispute that being our most reactive site?
What makes it more reactive than the oxygen is connected to the other carbon chain? It is a function.
Okay. So that's a fair dispute.
Isn't H3O charged?
Yeah, I would argue both Anthony and Ivan are looking at the problem from the entire backwards direction, which isn't bad necessarily. Okay, you are identifying lone pairs. You're looking for those electrons to run the reaction, but that's not the most reactive thing.
Do you
The
mean
most
the
reactive
H3O+?
thing is the H3O plus. And how does the H3O plus react?
As an acid.
What is an acid?
It donates a proton.
Okay, so what we're looking at is H plus. Okay, and for those really paying attention, now that we know we're missing electrons, what do we need to find?
And
A source of electrons, and now we go right back to Ivan and Anthony's challenge behind this. Okay? So if we're comparing these, you're now asking, the reactivity between the alcohol hydrogens, sorry, not hydrogens, that's just what I happen to draw. The alcohol lone pairs versus the carbonyl lone pairs. Okay. So, Anthony, what you suggest is, well, aren't they the same? Well, are they the same?
Not necessarily. Wouldn't the hydrogens on the oxygens be far more positive than the one that's connected to the carbon, connected to the carbonyl?
Okay, would the hydrogens connected to the oxygens, so we're talking about our alcohols,
Yes.
okay, wouldn't those be far more positive than the hydrogen connected to the carbonyl? Okay, we're going to run two tactics. First tactic, my response is, today is Tuesday. And if you're like, well, what the hell does that have to do with anything? Exactly the point. Why do I care about the acidity of those hydrogens? What did we say was the most reactive thing? H+, which means what do I need to find? The source of electrons. And you're now talking about the semantics of which hydrogen is more acidic or next most acidic. It being acidic would be H+. Well, is H+ going to do anything with the H+? No. Okay?
Well,
So that's why that argument isn't relevant to the system. Could we shift the question to now say which of those hydrogens is more acidic? Absolutely. Before we run that path, do we want to answer that question now or hold that, work through this question, and come back to it? Hold it. Okay. Back to the initial question that you guys are fighting over, okay? Which electrons are more reactive? The red electrons on our oxygen or the blue electrons on our oxygens? Okay? And the initial statement was, there's no difference. Is there no difference? Okay, if you're going to make the statement the red ones are more reactive, you are claiming that there is a difference. What is the difference? Okay, what we could push to is the pi bond. Okay, that pi bond is certainly going to change the reactivity of that red position versus the blue position. How could it change that chemistry? What could we look for, particularly when we see resonance? That was the answer. Shithead. When we see a pi bond, what could we potentially look for? We could look to resonance, and if we drew out the resonance, we'd be looking at a negative oxygen, admittedly a positive carbon as well, and that will come in handy and useful and relevant later, but we have a negative oxygen. So now when I'm thinking about which electrons are potentially more reactive, am I looking at the red ones or the blue ones?
The red.
Okay. So that could be a big step aside to say that's why we're going to focus there. Okay. No one's going to like this, but we're going to do it anyway. Are the blue ones still reactive? Yes. Okay. Could the blue ones lead to other products than what we're going to talk about?
Yeah.
Yes. What does that mean happens to our yield?
Goes down.
It goes down. And yield is something we rarely talk about in lecture. We only focus on the major product and kind of that path. But what we'll find, particularly when we encounter these types of reactions, which are actually equilibrium reactions, your yield starts to change significantly. And we tend to kind of ignore that and just float it to the background and not worry about it. Okay? Yield is absolutely an issue, and it can pop up and it can have an effect on our overall systems. What we're trying to do is focus on the primary chemistry, because the primary chemistry is more likely to advance to something in a larger amount than the secondary chemistry. Does that make sense? Yeah? Okay, cool. So we said the reactive thing was H+. Okay, we needed electrons to neutralize that H+. We noticed there were a bunch of electrons. We noticed that the red electrons were probably more active than our blue electrons. So we could now go through and start drawing a mechanism addressing how that should happen. Okay? So I've drawn resonance. Remember, when we draw out a mechanism, we're not supposed to be really addressing resonance as our source. We should be starting from our best Lewis structure. These two are related via resonance. This one's best, this one's useful. So the useful draws attention to the fact we have that negative oxygen. Now we can start connecting those pieces. But if I'm talking about my mechanism, I don't want to start my mechanism from the useful. So that means what I'm going to do is delete my curved arrow there. And I now want to add a curved arrow on my best structure to explain the chemistry. Okay. What do I want to have react?
The electrons from the pi bond.
Okay. Electrons from the pi bond, okay, we'll work with that. What are they reacting with?
The H plus given out by the H3O plus.
H plus. If we add a curved arrow, oops, that's an arrow, okay, we could then go through and draw out our product. What would our product look like?
And alcohol, right? It must be an OH.
Kind of, sort of. I'll accept OH. I like that. Show the green because we have that new bond.
And then the positive carbon.
Okay. We still have the lone pairs there, and we have the positive carbon. Do we like forming positive carbons? No. Why is it okay to form this one? Bless you.
First person.
Plus it's primary. No, not primary. Tertiary.
It's not tertiary. Technically, it's primary.
Oh, sorry. H. Yeah.
So we could draw out resonance. Ooh, that got real sloppy real fast. Too bad we didn't need that part, so let's not worry about it. Okay. And if we drew out our resonance structure, we could get something along these lines. With our new bond there, and we've now lost that positive charge. Okay. We again have two resonance structures. Which of those two is the best?
Technically, the one on the left.
Okay. So we've got a vote for the best being the one on the left. Everybody agree? Okay. I'm glad you all agree. You're all wrong. It's the one on the right. What? She said, didn't speak up. You got it. Oh, sorry. I apologize.
But I thought the oxygen wouldn't like being positive in this.
Ah, okay. So now there's the dilemma. The one on the right is the best. Why is it the best?
Is it because oxygen can hold the positive charge?
No, it
Nope.
would hold the positive charge the worst, wouldn't it? Because it's the most
Yeah,
electronegative.
oxygen's the most electronegative of that set. It should not be positive. So why is the one on the right better? Which is an ACS question. They ask this all the time.
Is it because of the pi bond?
No, not directly. Okay, Josie, you liked the one on the right. Do you know why you liked it?
That was like my reason was the pi bond too.
Pi bond's kind of a secondary issue.
Is it the resonance stabilization?
Because of the
Oh, you gotta give me more than that.
Because the really unstable is primary.
No.
But wouldn't carbon be more likely to make a positive charge compared to oxygen? Because it's less electronegative than oxygen? Okay, what the hell even is that?
Octet.
An octet.
Octets.
I thought you were trying to draw a hand.
He's looking for the 8-fingered man. If anybody gets that reference. Okay. Octets. Okay. That's why the structure on the right is the best. Okay. Which is going to introduce a potential issue. When we talked about our very first step of the mechanism, which structure did we start with? We started with the best resonance structure. So when we go through to draw that mechanism, which of those two structures should be the product of my mechanism? The best one. And if we push what Anthony suggested, which I completely 100% agree with, for the record, I'm wrong, but I agree with you, the pi bond is higher in energy because you're looking at p orbitals than the lone pairs sitting in sp hybrid orbitals. So we might think that the pi bond should be the one to react, pick up the H+. Okay? That's using a hybrid orbital argument. If you actually look at molecular orbital theory, Non-bonding electrons are higher in energy than bonding electrons. Period. Okay? Okay, so what does that mean? The mechanism as we are drawing it is technically going to be wrong. And so if SmartWork asks you to draw a mechanism, it's going to have a problem with this. Okay, because you're showing the pi bond react. The pi bond isn't the primary source of electrons in this reaction. What we should instead be sourcing for our electrons would be
The lone pairs.
the lone pair. Which means if we're looking at our reaction arrow, we're not going to that one, we're going to this one. And we could go through and say resonance helps to explain why that structure can come into existence. Kind of, sort of?
But isn't a positive oxygen less stable than a positive carbon?
It's coming down to the rules of Lewis structure. And our rules of Lewis structure is octet trumps everything. Okay? That carbon is missing its octet. It is therefore the most reactive thing present. We need to neutralize that as quickly as possible. The best way we do that is by, yes, giving the oxygen a charge. Okay? Does that mean the useful structure isn't something that we should be using?
We should still
It's useful.
We should still use it. It's useful. It helps us to see the chemistry behind this. We know that oxygen doesn't want to be positive, so what is it going to do? It's going to take electrons from that pi bond. Okay? That's going to set us up with our useful structure with the positive charge on the carbon. How do I neutralize the positive charge on the carbon?
by taking electrons from the oxygen.
With electrons. So we could take the electrons from the oxygen, but then all we're talking about is I want to fix my oxygen by taking electrons. I want to fix my carbon by taking electrons away from the exact same atoms, and all you're doing is the two-step. If that's a two-step, I don't know. We're just going backwards and forwards. That's not very useful. Okay? So where else can I get electrons?
From the hydrogen.
What charge is the hydrogen?
Positive.
And if a hydrogen is positive, does it have any electrons?
There's the other structure of the reactor.
So we got to go out to the other reactants, and in the other reactants, was there a source of electrons
In the OH.
in the oxygen of our
Yeah,
alcohol,
and the alcohol, yes.
okay, which we had originally referenced? I'm going to try and stop drawing it out as CH2s and do the zigzag.
Well, now
Actually, I'm going to do it now.
the question is which positive charge does it react with,
Fair. You should be able to answer that.
right? Should be oxygen, right?
Okay. Should these electrons share with the oxygen? Don't draw that. I see that pen. Should that oxygen share with the other oxygen? Why not, Abby?
Doesn't feel right.
The vibes aren't right.
Exactly.
Okay. So I said you can't draw it, but that doesn't mean I can't draw it. But I'm not going to draw the whole bloody thing, just for the record. Okay. And also for the record, I'm going to leave that pi bond alone for the moment. You just saw the issue.
Yeah. Okay. Well, the same thing. Okay, I get it. Yeah.
Does everybody else see it? If that oxygen comes in and shares, what happens to the octet on our oxygen? We've exceeded. You could say, well, can I move the electrons in the pi bond towards the carbon? Okay, that's fine. You could do that. We already addressed that it shouldn't do that, but let's just say, whatever, fine, let's do it. Mike's an idiot anyway. Let's just go for it. Okay, and we move those electrons towards the carbon, and what happens to the carbon?
Becomes negative.
Is the carbon being negative a good thing? No, that should be an insanely big red flag at multiple levels. Carbon is not electronegative, carbon is small. There's no resonance to stabilize that. Okay, on top of which, just lost the train of thought. Son of a. Just.
I don't know if the oxygen stick with hydrogen.
I just lost the train of thought. I'm sorry. No idea where it went. Okay, but ultimately, what does that mean? Okay, the oxygen's not in the positive. Okay, trying to figure out our reactive positive, where should we look? Should we look at the best structure, or should we look at the
The use.
the useful, and when we shift to the useful, we can see where the positive is actually building. That's why the useful one comes in handy, because it helps us to see that reactivity. What does that mean for us? All that stuff I drew, which I told you not to draw, right? Give me some credit. Okay, we erase all that, and we should have our lone pair come in and attack there. Okay?
You say attack there, not like backside attack, is it?
Okay, and it's not technically backside attack. Why is it not backside attack? This may have actually been in one of our recordings.
It's not really a nucleophile?
It's absolutely a nucleophile. It is absolutely an electrophile. That blue oxygen is sharing electrons. It's donating electrons. That makes it a nucleophile. Whether it's strong or weak doesn't change anything there, unfortunately.
It's too big.
Nope.
Well, that was all the things I could think about it.
Okay, so you just say pass.
Abby, come on, bud.
I didn't say you had to call out names.
You
Jesus.
said pass. You
That's
didn't
rude.
say not to call out names, so there we go.
Is it an S, wouldn't it be an SN1, not SN2?
Nope.
No? Completely lost.
Okay, so completely lost. Fair game. So let's rewind back. What kind of reaction is it?
That's supposed to be an addition.
Oh.
We're looking at carbonyl additions.
And if it's an addition, we're not talking about substitution, backside attack, any of that. What's reacting in the addition?
Pi bond
The pi bond. And where's the pi bond located?
on the backside.
Yeah, not on the backside. That's a decent answer. Above and below the plane. So when we're talking about this chemical reaction, your carbonyl is effectively a flat structure. Your pi bond is up here. The nucleophile is coming in and reacting up here from the top. Not from the back side of that bond, but from the top. Okay? Or from the bottom. Okay? This starts to get a little weird. Is that why you're laughing at me? Jiminy Christmas. Okay? It's not coming in on the back side of that. Okay? Kind of, sort of?
Say who your favorite painter is.
Jesus. So, ta-da! Is that a product?
I mean, the option is positive.
Which means,
We're not done.
cool. So, fix it. Okay. If that oxygen is positive, it's going to want to steal electrons from somewhere around it. It could steal them from our green bond. And what does that mean? Equilibrium. Okay? And this is why this particular reaction is so nasty. Okay? All of these steps that we're going to talk through, and I really didn't size this out properly, okay, are equilibrium. Okay? We could try and pull it from the blue bond down to the carbon, and if the oxygen steals electrons from there, our carbon becomes positively charged, and we'd have a primary carbocation. That's not very good. Okay? If we steal them from the hydrogen, what do we end up producing?
Hydride. No, not hydride.
Just H+. Right? Was H+ okay to have in the solution? I don't know. What was the very first thing we identified as reactive?
H+.
H+. Okay? So it may not be super stable. It is going to be something that's reactive, but it's at least fitting the pattern of what we already have. Okay? So now what's the deal?
There isn't a deal. Wouldn't that just be it?
So there's a potential argument. We could go through and say, well, now isn't that it?
I mean, the only other thing in the solution is water, because of the H3O plus given the hydrogen. There'd be a little bit of water.
There would be a little bit of water.
And then obviously the H plus floating around.
Ooh, I still have H+ floating around.
So we form H2 and H2?
But
There's no H2, because to get H2, I need H-. We've not established an H- anywhere through here.
the thing is, if a hydrogen tried to attach any of those, it would cause a positive oxygen, which oxygen is really
Cause a
not-
positive oxygen. Cause positive oxygen. So if you're going to go through and say, I don't want to do this because it makes a positive oxygen, our entire mechanism
Hold
forms
on,
positive
hold on a
oxygen.
second. But this doesn't, it shouldn't end in a positive oxygen, and if we continued from here, it would go into a
So it shouldn't end in a positive oxygen. So that's an interesting statement, and I can accept that one. Okay. If we had the lone pair or green lone pair on that oxygen pick up a hydrogen, it would give us a positive oxygen. And what could it do? It could get rid of it, okay, neutralize, lose the positive oxygen, which generates another positive oxygen, which takes us backwards. Okay, so we could do that.
So then all of this is just equilibrium?
Is every single step in this equilibrium 100%? Yes. This is one of the reasons why the end of this discussion is going to be how else could we do this without having to go through a mechanism where we end at a neutral structure that looks remotely stable. Okay. It's still equally reactive. There's still H plus floating around. If I react that oxygen, what happens?
The same thing?
I go through the same stuff we've already done. Okay, well, are there other oxygens?
A couple.
Yeah, so what should we do?
React with those.
You should react it with those and see what happens. Okay? So what we could continue to do is try and propagate those out and figure out which one of those would potentially react with our positive hydrogen more. This is going to be an interesting dilemma because what is the difference between, we'll call it our blue oxygen and we'll call it our red oxygen?
Drops the distance to another electronegative element.
Okay.
Because there's an oxygen betwixt the two, and the red one's closer than the blue one, thus red one is. I don't like that look, but therefore the red one is more stable because of induction, or less stable?
Okay. So what you're trying to say is that this green oxygen, if we will, is closer to the red one, which is doing what? It's withdrawing electron density. If it withdraws electron density, what happens to the electrons around the red oxygen? Becomes more positive. If it's more positive, can it share electrons with the hydrogen?
No.
No. Which would then suggest
It's worse, the blue one.
it's worse than the blue one, then we should run the blue one. Okay? And we go through and run the blue one, we're going to find that it doesn't really take us much of anywhere. It kind of stalls out as a reaction. We get a positive charge on that oxygen. We don't want to form a primary carbocation, so it just kind of sits there and oscillates back and forth. Okay? Is there another explanation we could look at with the red one? Because you made an argument of induction.
Which is not high on the list.
Is there some other argument you could potentially make? And this gets a little vague and challenging. What could our green oxygen do if not induct? Could it resonate?
Don't fucking even. Seriously?
I'm asking!
Is this, I swear to God, this keto-enol tautomerization bullshit. I swear to God.
It's not a keto-enol tautomerization.
Okay, thank
I would
you.
argue it's worse.
Okay, well.
Can it resonate?
Yeah.
Let's try that again. Can it resonate?
No.
No. So there isn't really the resonance potential here. That oxygen could theoretically kind of donate electrons in, but it doesn't really do much for us. Okay? The blue one we said was kind of a dead end. Well, let's see what happens with the red one. Like, just giggles. Okay? It's equilibrium. Equilibrium 152. That was some fun stuff. We just played around. You just throw stuff at it and see what happens, right? So if we did this, what happens? Okay, remember we said this could be reversible here.
You get a O plus.
You get a positive oxygen. Does oxygen want to be positive?
No.
What could it do? Say that again?
Why couldn't the other one leave then? If that one could, why couldn't the other one?
Why could the other one not leave? I gave the answer. I didn't draw it out. But I did give the answer.
I see very little reason for it to not leave.
Form a primary carbocation.
Oh, son of a bitch, and that one is and this other one is okay.
And if that leaves as water, which is the same argument we can make down here, the blue one, we'd be forming a primary carbocation. Up here, we're forming a primary carbocation.
No.
It's a little gray area. Technically, yes, it is connected to one carbon, but
There's an oxygen also, which has
there's an
more
oxygen which has the ability to
Resonate.
resonate. So the resonance option isn't something that is explicit right out of the gate. It's a follow-up on that reaction.
This sickens me.
Okay, so that's a fair statement.
I don't know if that counts as its starting structure. It seems to be a couple more carbon than there was before.
Well, there's the rest. Just revert back.
Okay, because if that left, we'd form a primary carbocation, but there's resonance stabilization. Remember, best versus useful, should be showing the best, so we should actually be showing that lone pair having shifted in there, and we would have our carbocation, a positive charge on our oxygen. Does oxygen want to be positive?
No.
So what could it do?
Take the electron.
It could take the electrons from the pi bond, but then the carbon is positive. So what does it need?
Electrons.
Electrons. And we got an oxygen with electrons, right? That red oxygen shares electrons, and we just go backwards. Seemed a bit silly.
Oh, is that where it ends now? Is that where we get?
That's charged.
Well, if it broke from the sigma bond, it would just revert to the starting structure.
It can't break from the sigma bond, right? Because what charge would that carbon become?
Positive.
Positive. And we'd have a primary carbocation. Can that happen?
Not normally.
No. So we can't take the electrons, for the sake of video at home, from that green bond. That's not a good choice. Okay? If we push on that even further, that's not a good choice because the pi bond is higher in energy. We should be focusing our energy on that pi bond because
Maybe
that's
that
the
other
most
signal
reactive one.
with the ring.
But why? When we talked about breaking that sigma bond, why were we allowed to break that bond?
Oh yeah, shit.
We had a resonance stabilized structure. Okay? And we're missing that resonance stabilized structure, so let me draw that up here. And I'm hoping I can fit my product-ish right there. We'll see what happens. We'd have our positive carbon there. Right? We said, how could we stabilize it? Well, we got the red oxygen. It could donate electrons. That takes us backwards. That's not useful.
Can't we just use the blue molecule again?
Wait, you mean there's another source of electrons?
Yeah.
And that perhaps, maybe if someone was a bit less rude in how they drew things and acknowledged perhaps this shape,
God, it makes a ring.
That's not where it was going, but I'll go with it anyway.
And then it. Okay, I see. Yeah, no, that sucks. That is worse than tautomerization. Completely agree.
okay? And now what happens?
Get a.
I officially can't fit it right there. It's going to have to be 2 steps. So it'll be 2 steps where the second step is the loss of an H+. We'll break that one down here in a second.
So it's a
I keep wanting to draw freaking sulfur. God,
Wait,
it's
it's a
killing me.
5-membered ring connected to a 5-member ring. Oh, okay.
Okay.
And then another oxygen.
Yeah, I'm working on it. I'm trying. Well, now I made it a dot. It's supposed to be a oxygen. Oxygen that had a hydrogen on it. There was that new bond that formed. Our oxygen would be positively charged. Our other oxygen picked up a lone pair of electrons from the breaking of that pi bond, right? We'd have a positive oxygen. Do we want a positive oxygen?
No, so
No. So what happens?
it would get rid of the hydrogen.
It gets rid of the hydrogen by doing what? Water comes in, acts as a base, removes the hydrogen. That's that second step. And what we would get, and if we wanted to be nitpicky with our lone pairs, we would now have this as our answer.
Wait, so is this one not equilibrium?
Officially, it's also equilibrium.
Okay, because you put 2 arrows towards it. Okay, nice.
Yeah.
And then there's 2 different steps.
Okay. So in this approach, what we have done is worked through all of the individual chemistry to think through all of those individual steps. Does that take time? Yes. But the intent behind that taking time now is trying to learn what happens with it, and then with a little bit of practice, you can start to skip the steps. Okay? Theoretically, with enough practice, you can skip enough steps that your whole picture changes. Okay? And instead of this version, which is now scattered all over the place because we had to loop back on ourselves because I didn't draw the right size, Okay? We could skip it and simplify it down to some real kind of core fundamental pieces behind it, which is really where kind of our primary chemistry happened. Okay? We start with, can I get away with red circles? Yeah, let's get away with red circles. We have a neutral structure. Okay. Actually, before I do this, are we good with everything that's up there? Because you're about to lose it.
Oh, let me take a picture.
Yep. All right, but what we want to go through and do is simplify this down into the nuts and bolts approaches behind this, on particularly where we had stump and challenges. Okay? We had a little bit of a stump and challenge to get started on this, but once we got started with it, we were okay with that next product, okay, with our best useful system. So that's straightforward. Let's delete it. And the next one was straightforward because that was charged too, so we needed to fix it. Which then meant we got to that corner, and that particular corner structure we really didn't like moving away from. That was a problematic structure. So let's hold on to that structure for a bit. Okay? And we processed through that and said, well, what if this happened? That sets us up with a new charge state, which then moved us all the way through to that final thing. So really, if we do enough practice, hopefully what we see is that we really are only talking about 3 points that we really care about. Our starting material, this neutral structure in our lower right-hand corner, and our final product.
So,
Right?
reactants, intermediate product.
The issue with intermediate carries a whole bunch of different terminology with it and a lot of baggage. It's not that you're wrong. It carries a lot of baggage with it, so I don't like using the word intermediate. Okay? So what I want to do is I want to change the approach now and say, how else could we have done this? Yet it's not at all what I wanted you to do, computer. Oh, well. Okay, so I'm going to delete everything. Sorry. We good with that?
Sure.
Okay, here it all goes. Maybe. Bye-bye. Okay. And where we could have looked at this was looked at the bare bones kind of chemistry behind what the overall system is. Okay. What we're starting with here is a carbonyl. Okay. That's kind of what started this whole cascade. That carbonyl was mixed with something. What was it mixed with?
Mixed with a couple of things. HDO plus.
The H plus started it, but if you track the mechanism all the way through, guess what happens? That very last step, what did we produce?
H plus.
H plus. Is the H plus actually doing anything?
It's a catalyst.
It's a catalyst. It's only being used to facilitate all of those individual reactions. Okay? So the H plus isn't actually critical to the overall picture. It's critical to the reaction working, but it's not the overall picture. I want the overall picture. What did the carbonyl react with?
The OH in this in the
It reacted with
alcohol.
an alcohol. Okay? An alcohol connected to some R group. Okay? In that reaction, what happened? We ended with our neutral intermediate, if you will. Then what happened?
One of them left? Oh wait, there should be. Because doesn't this complicate it a little bit, considering there's supposed to be a third oxygen somewhere and not an important detail to not leave out?
Yeah, so what did it react with? Say again?
Yeah, the same thing. The
I'll sort of accept that. It reacted with another alcohol.
Oh, okay, I get what you're doing now.
And what happened? We produced H2O and some hand drift, ROR, and ROR. Okay. Is this what actually happened in our reaction? Did I add 2 different alcohols to my structure?
Not technically, no. I mean, you did, but not. guess so, you did just add 2 alcohol.
The 2 alcohols were connected to each other. I don't care what the hanger-on is. As long as I have that functional group, the rest of those hangers are just out there. They could be separate molecules. They could be connected. That's irrelevant to the overall picture. The overall picture is just that there's an R group out there.
And then the last step, it makes its little ring.
Right? And then in this particular case, it looped back on itself and it formed that ring. Okay? Because the R group off of our blue oxygen was a CH2. The R group off of the red oxygen was a CH2. Those CH2s were connected. Ta-da, there's the ring. Same system. No difference. Okay? The next layer to add behind this, all of these were equilibrium reactions. We could go backwards and forwards through the whole entire process. So if we now look at all of our structures, this is now our overall picture. And so what we can say is when I see a carbonyl, close enough, okay, that carbonyl can react with an alcohol to make a new structure. But if I'm going to call it a carbonyl, and I'm going to call it an alcohol, I better have something better to say than a new structure. What do I want to call that new structure? Let's call it Sally. Sally reacts with another alcohol to make Harry, right? Because Harry met Sally.
You're old-timey, whatever you're on about. I have no clue.
That's fair. Right? We just invent names for these things. Okay? The names that we invented are talking or looking at this thing saying, I'm starting at a carbonyl, and the carbonyl passes through an intermediate. Okay? And if we look at the mechanism, it passed in the halfway point to that mechanism.
So now you want to call it an intermediate.
Okay? Yeah, I know. Okay? And if it's passing halfway through that mechanism, I might call whatever this structure is half of whatever this is. Okay? What is half? I could call it a hemi. It's hemi of whatever I want to call this. Well, what do I want to call this? Okay? I'll call it an acetal. And that this is now a hemiacetal. Why? It's just the same as Harry and Sally. It's just what it's called. Everybody calls it acetal. You run around and call it Harry. Everybody's going to be like, what is wrong with you? Okay? Are you freaking old? Okay? Those were the names we addressed to them. So what we would now try and do is go back and match to our reaction. Well, when I look at this reaction, what do I see? I see a carbonyl. Yes. Do I see an alcohol? Yes. Do I see a second alcohol?
Yes.
Yeah. Okay? And that gets weird because you're looking at one molecule being, but they're connected to it. It doesn't matter. They're still connected. That's 2 alcohols within that. So this reagent system matches this pattern. So if I've memorized this pattern, I don't have to draw out all the mechanism. I can just go, poof, this is what's happening.
So it's an addition and then a substitution? Because that's what you're doing on that second step.
Yes.
Oh, okay.
Yeah. Okay. And if you go through and watch the lecture video on it, which is a play pot, we'll come back to that in a second. It's the least liked play posit of all play posits I've ever done. Like, everybody freaking hates it. Like there was a mini riot once. I think things were thrown at me for it. So just for the record, watch out for that. It's a painful one. It addresses those pieces and it looks through the mechanistic detail behind how it goes through and works, which is what we just walked through and did. Okay, so we just spent 49 minutes looking at. That video does, I think, in 30. I think it's a little bit less. Okay. It also adds some more detail about some other pieces behind it, but that's the ultimate section that you're just kind of breaking down behind it. Okay. And if we know those patterns, we can just drop those patterns directly on top. And if we haven't bothered those patterns, then we have to memorize that process. And if you aren't going to memorize that process or understand that process, those are your two options. You either understand it or you memorize, and that's it. That's all you get. Okay? I will say we can throw other questions at it that if all you've done is memorize this in black and white, you've got a problem. Okay? This black oxygen is the carbonyl oxygen. Okay? Very carefully color-coded through this system. And what they can say is when I take this carbonyl and I react it with this structure and this oxygen is labeled, okay, radio labeled as oxygen 18, because most oxygen is 16, so we add 2 more neutrons, it has a different mass. Where does it end up in the reaction or in the products? And they could say, is it the water or is it the acetal? And so if you don't know the mechanism or the color coding behind this, you can't answer that question appropriately and you end up just guessing. Okay? Kind of, sort of? Ivan, are you good?
Oh yeah, I understand. I got a question. Nice.
We were supposed to come back to a question, I think, weren't we?
Oh.
Which hydrogen is most acidic?
Yeah. something
Which
about-
hydrogen's most acidic?
Yeah.
Oh, yes, I remember now. But first,
In the book, it says something about if we change the axis or like the quantity of each, like of the reactants.
fair play. I know exactly where you're going. You don't have to keep going on it unless you want to. No? Okay. These were all equilibrium reactions. If they're equilibrium reactions and I start with those reagents, how much product do I get?
Small.
Okay? Officially, it's going to be dependent on the equilibrium constant for that reaction. Okay? But for the most part, we're looking at relatively small amounts. Okay? Why would they be small amounts? The equilibrium constant's pretty close to 1. Why is it close to 1? Is there much difference in energy between a carbonyl and 2 alcohols versus this structure with water?
Not really.
The energetics between those two are relatively similar. You don't see a huge favoring of reactants over products. Okay? So if I want to make the acetal, how do I do it? Because if we just set this up and I get a yield of 50%, that's a pretty trash yield. I want to make it better.
Well, I was about to say, couldn't you add light to more easily break that pi bond?
Nope. So the easily breaking the pi bond, you're talking about adding an acid catalyst. You can add an acid catalyst. What is the acid catalyst going to do here?
Oh, I was
It's going to be just as equally likely to protonate and allow that to come off as a leaving group and go the opposite direction. Oh, light. No.
No.
Light, nope, sorry.
Isn't that what breaks pi bonds?
Light can excite the electrons in a pi bond, yes. Is that going to do enough to do anything with the reaction? No. It's a nice try.
Heat.
Heat will speed me to the equilibrium, but it's not going to favor products. Okay? And this is where everybody's favorite class comes back and haunts them.
152.
152. Because what we're talking about is how a reaction favors products. If I've got A plus B in equilibrium with C plus, not B. I know my alphabet. Thank you for telling me that, whoever mumbled that.
If you have an excess of A and B, you'll get more C.
So there's where we got to be careful. If I just add in more reagents, does that work? Not really. That's not changing the equilibrium to favor products. That just means I have to put in more starting material to get more products.
There's something.
Yes, there is something.
Yeah, there is something about this that I remember, but it's not
It's not adding more both products. It's adding more one product. So if I increase the concentration of B, the equilibrium is going to shift to decrease that concentration to bring it into balance. Okay? Because I have a limited amount of A, it's going to start forcing the formation of more of C and D. Okay? So increasing the concentration of one of my reactants will push me to make more products. Okay? Since we started with that, which reactant should we increase? Carbonyl, alcohol, or acid?
Well, wouldn't the acid mean nothing because it's remade at the end?
Lovely. The acid as a catalyst has no ultimate effect on the balance of our equilibrium, so the acid doesn't change anything, so it's going to be the carbonyl or the alcohol. Which one should I increase?
The carbonyl went up.
Right? Does it matter? Is it going to increase the yield?
Yep.
Yes, it will. So in the grand scheme of increasing the yield, it does not matter. Does it still matter, though? Yeah. Why? When we talk about our experiments, is the only thing that matters yield.
Sometimes.
And even if we think through our labs, most of our labs, we should go, oh, well, it's just, I get a melting point, prove I made it, and I get a good yield. Like, ta-da, it's done. That's the end of it. Okay? One of the things that becomes less obvious is the backstory that goes into it. Okay? We did a limonene lab in OChem 1, okay, which you may, did limonene sound familiar to you? A little? Okay, so we isolate a compound from oranges. Okay? Have you heard of deadly nightshade?
Yes.
Yeah, okay. Okay. That's a plant that produces a toxin. Okay, why didn't we isolate that toxin instead of limonene? But it's the same principle. Why can't I choose that experiment instead of limonene? I don't want to die. What's one of the other consideration that goes into
Price.
designing things? Some of it comes to price, some of it comes to toxicity. Okay? So how would I decide which chemical I should put in the larger amount? Look them up. Which one's more expensive? The one that's more expensive, don't use a lot of that. Okay? Use a lot of the cheap one. That's going to push my equilibrium, and I'm now not burning money in that process.
Well, no.
Because that excess of alcohol isn't all going to go away. It's still going to be sitting in there. Okay? Or the excess of that reagent isn't all going to go away. The other one will go away. And if it was more expensive, let's consume the expensive one to produce my product.
Well, now that leads to the question, which of those is more expensive?
So how do you decide that? Well, you would look it up. Okay? I'm going to bet the more expensive one is the aldehyde. Why? Reactivity, your alcohols are relatively more common. Okay? And that particular alcohol is commonly used as a substituent group, a protecting group in your acetal system, which is another application of what we could use acetals for. Okay? What else could you do as far as the equilibrium goes?
Add the products.
Wrong word. Take out the products. If I add products, what happens with the equilibrium? If I increase this, it goes that way. I don't want to do that.
Hey,
I want
products is
more products.
relative. Maybe I want A and B from C and D.
Fair play. Okay. So depending on what you are trying to do I want the acetal or do I want the carbonyl? I can add or remove individual species to push that equilibrium one direction versus another. Okay? How does that become dangerous for you to try and interpret? If we look at that reaction, does it say excess of the alcohol? So how do you know it's in excess? It's an appropriate answer. You don't. Right? You would know because it wouldn't make sense to run as a reaction if it wasn't. That's it. Right? Which means you had to understand all of the chemistry and the equilibrium stuff on the back end. Okay? Are there other things that affect equilibrium? Another fun favorite word that you learned theoretically in 152?
Pressure. No, what am I thinking?
Entropy.
Oh.
You could look at
yes.
entropy effects for that overall reaction. Okay? And if we started with how we've got it shown here, where these are two unique alcohols, we start with 3 particles, we end with 2. Which means we did what to the entropy?
Lowered it.
Is that a favorable thing to do?
No.
No, entropy is supposed to go up in a reaction. Which means if I start with 2 separate alcohols, the likelihood of making the acetal decreases. Okay? But if I switch to this, I only have 1 molecule that's acting as the alcohol, which means it's a net 0 entropy effect, right? Which could increase the odds of me being successful by playing with equilibrium.
Yeah, I still never got entropy in 152.
Okay.
I never understood it.
I don't blame you. That, by far, was the #1 worst lecture I've ever given, was a lecture on entropy. Yeah, horrible. Absolutely horrible. Bless you. 10 minutes into a 75-minute lecture. I give up. I don't care, sitting on the front of the desk. Like, you're just going to have to figure this out. These are the answers on how you do this. I don't know why. Like, that was the lecture. Oh, it was painful. And nobody got up and left. Like, if they got up and left, it would have been so much better.
They stayed there?
They just stayed there while I was like, this shit sucks. Good luck. And just stared at me. Yeah, it was so painful. Oh, it was so painful.
How long ago was this?
It was my very first class.
Are you tried to do entropy your first class? Or is
No.
Oh, you're
I got hired as a teacher at ASU
Uh,
with the thought that they would have me teach organic chemistry because that's what I'd been teaching for the last 5 years for them. And they were like, oh, we need someone to teach 152. So here, you can teach it. I was like, I haven't even done anything with that class in probably 10 years. They're like, yeah, but you're good at chemistry. You can figure it out. I was like, you guys are so fucking rude. Okay. And it was the week before classes started. Like, it was,
oh.
yeah. I think ASU treats you as a number. Just work for them. Whoa, man.
You have to report it down.
Delete. Okay, in any case, some conversations that we should steer away from. Acidity. Aldehyde hydrogen versus alcohol hydrogen. We'll make that a CH3. Which one's more acidic? Okay. And this is a very challenging one. It is one that is also commonly tested on the ACS as well. Okay. When we go through and discuss acidity, okay, the very first thing we talk about is that we should look at the conjugate base because the conjugate base allows us to see the reactivity. So if we go through and run the reaction, it's going to produce
Oh, definitely the OH then.
a negative carbon, H+, versus a negative oxygen, H+. Okay?
You couldn't do resonance with that other one.
And there becomes the real kicker. 9 times out of 10, when a student goes through and says that the aldehyde is more acidic, they say, oh, it's resonance stabilized.
Well, that would make it less acidic. But it's not resonance.
The conjugate base is resonance stabilized. They go, oh, you can do resonance. You can just move those electrons up there.
No.
Okay? And this typically comes up even more so in second semester. And we'll see it at the very end of the unit because there will be this structure that we'll talk about, which is one of my favorite ions, and we'll run the joke now. Okay? Getting this structure in black. Okay? It's one of my favorite ions because it's known as the acylium ion. Silly? It's a silly ion? Is that the result of that arrow? Yes, we're trying to make the triple bond, okay, with the CH3 down here, but what happened to the oxygen?
You exceeded its octet.
It still has 2 lone pairs. You didn't move those lone pairs, which means the octet has been exceeded. Okay? So this comes from, well, I know there's a structure that does resonance, so I'm going to make it that. You can't do that. That's not how it works. Okay? You have to be able to draw and say that this does indeed work. And if it doesn't, then it doesn't. There is no resonance for this. Whoops. Contempt. See? There we go.
Maybe that's what I'm going to do. If I don't know how to answer a question, I'm going to turn into something I know how to answer.
Okay, which is lovely, except it won't answer the question. Okay? And if we look at the other one, we're looking at negative oxygen versus negative carbon, and we go, oh, okay, well, negative oxygen makes sense. That's the more acidic one. Okay? Kind of makes sense? Cool. Let's throw in a monkey wrench. What about the purple hydrogen?
Isn't, oh, God. Yeah, then
So-
that one is resonance stabilized.
So what
Yeah.
we should go through and do again is remove the hydrogen. We look at the result. What do we get? Negative charge on carbon. You go, oh, can't have a negative charge on carbon, except
It can be resonance stabilized.
it can be resonance stabilized. That resonance stabilization actually falls back on your favorite statement that you made earlier today, which is kind of fun. We're looking at effectively the enolate. You're looking at your kind of keto enolate keto-enol tautomerization behind that
It
process.
always comes back.
Okay, so that purple hydrogen is actually fairly acidic. How acidic is it? It's about the same as the blue, okay, if not slightly more. Why? They're both forming negative oxygens, except the purple one has some resonance stabilization, admittedly onto a carbon, which isn't great, okay, but our purple hydrogen is slightly more acidic than the blue hydrogen. Neat. Okay, and resonance helps us to see that. But we have to make sure that we draw our arrows appropriately, okay? And we draw those systems appropriately. That's the approaches that you need to be tackling, that process behind it. Make sense? Does that help you with that? Questions on that question? Okay. Because we did this in the tutoring center, I'm going to do it here. When we talk about the acetals, okay, organic chemistry, I think, kind of goes about it wrong. It's not really wrong, but we look at it as this kind of synthetic system. It's a horrible synthetic system. Why is it a bad synthetic system?
Reversible.
It's equilibrium. Okay? It's equilibrium with no real strong defining directionality with it. Okay? So that equilibrium system makes these reactions very inefficient. Okay? They can be leveraged and used. Carbonyls have a pi bond. Pi bonds are reactive. If I react that carbonyl with alcohols, I can turn it into an acetal. Do I have a pi bond anymore?
No.
No. Which means if I run a reaction that is pi bond susceptible, my carbonyls would react, but if I can convert my carbonyl to the acetal, it no longer reacts. Okay? This introduces the concept of protecting groups. Okay? These alcohols can act as protecting groups for the carbonyl, and then when I'm done with whatever that reaction is, I can reverse it and get my carbonyl right back. Okay? So that can be kind of nice. So you get this idea of protecting groups. Protecting groups as a whole are kind of a crude implementation. Okay? Really what's happening with protecting groups is you're doing a whole bunch of chemistry. There's a bunch of chemicals and reagents within that process to make it, so that you can do something else, and then what do?
You turn back.
Undo that stuff. Okay? So if I want to walk forward, first I walk backwards, then I get to walk forward twice, or I guess 3 times, and then I get to walk backward once. Did I make it forward? Yeah, but I threw in a whole bunch of extra stuff that I didn't have to do. With walking forward and backward, it's not that big of a deal unless you had to do that for every single step. Then it would be exhausting, right? Okay? For chemistry, why is it a bad idea?
Because chemicals are expensive.
Those chemicals cost something. You have to buy those chemicals. They're now dirty. You have to now dispose of those chemicals. Well, now you have to pay someone to dispose of it as well. Okay? What if those chemicals are potentially toxic? Okay? You've got the toxicity that folds into it. Every time you run a reaction, you don't get perfect yield, which means every reaction you run, you lose a little bit of your product. And if I have to run 2 reactions on top of doing another one, I'm losing a whole hell of a lot more product. Okay? So synthetically, protecting groups are kind of, it's recorded, why not? Everybody hates me anyway. Are kind of lazy. Okay? Ultimately, what it means is that whoever was trying to do that synthesis decided that they couldn't figure out a better way, and so they just said, I'm just throwing some protecting groups, take it off. I don't care about the environment. Screw the dove. I don't know. Okay? That is increasingly becoming problematic, and we're starting to realize kind of repercussions of that, which is where you'll hear reference to green chemistry. And green chemistry is trying to leverage how we approach synthesis to minimize, okay, safety risks, waste risks, all of those fun, nasty things. Okay? So you can look at the efficiency of the reaction. The reaction is horrendously inefficient to run that process. Okay? And you look at how much actually made it to your product, and you compare that to where you started. To run a protecting group, you've had to throw in a whole bunch of extra stuff that didn't make it to your product. That's not efficient. Kind of make sense? Okay. Oh, okay. Why is it actually relevant or important? Okay. Well, it becomes relevant and important for a particular molecule that I can't draw by sight, but we'll ballpark it and enough people will hopefully be able to recognize it. Josie said, What did you say?
It looks familiar.
Looks familiar. What does it look like?
Whole lot of hoopla.
I can't do hangman because the people already know the answer. It's not fair.
Oh, glucose.
It's glucose. Okay? And why is it important? Well, we just talked about carbonyls, acetyl, hemiacetals, all that fun stuff. Why should I bring in glucose as a conversation about this? Do I see a carbonyl?
No.
No? So I was stupid. Why did you talk about it, Mike? Well, because I'm not talking about the carbonyl. What am I talking about?
Alcohols.
Okay? The hemiacetal or the acetal. And if we look real carefully, the difference, our hemiacetal has a carbon that is connected to 2 oxygens. The acetal has a carbon that is connected to 2 oxygens. So what those have in common is there's an atom, a carbon atom, connected to 2 oxygens. And if we go through and look at the glucose structure, hopefully what we see is there is a carbon connected to 2 oxygens. Okay? And we look at glucose in its kind of monomeric form is a hemiacetal. Okay?
Wait, but isn't there? Oh wait, never mind. I was about to say, isn't there 2 carbons that are like that? But
No, there's just that one. Yeah. Okay? And I may have bollocksed the structure. We'll find that out later. Okay? When you take biology or biochemistry. Okay? But one of the things we'll find was, what do we use glucose for? Energy. Okay? And we don't just store it as individual glucose molecules. What we do is we attach glucose molecules together in a chain. Where do we connect them? Okay, there and I believe out here. And when we connect this in a chain, that hydrogen is no longer a hydrogen, it becomes the carbon of another structure or another glucose. Why does that become important? What do we now have? An acetal. And if we're looking at carbohydrates linked out in this change, okay, we've got acetals. Neat. Okay? That's why it's directly relevant for pretty much anybody doing any kind of medical pathways. You're going to see it show up in biochemistry and when you talk about carbohydrates. Acetals are part of that. Okay? Why else do I think it's kind of neat and fun to play around with? How many atoms are in that ring? 6. So we have a 6-membered ring. And 6-membered rings from Unit 1, or not Unit, Unit 1 and OChem 1, we know are better represented as?
The boat thingy or the chair.
The chair, not the
However you
boat
want.
thingy.
You can call it a lot of things. It kind of looks like, that's not a boat, but still.
Okay, we've got a chair. And if we care about that carbon, that's going to be this guy right here, we'll note that that OH could have been up here, or it could have been down here. The rest of the OHs are locked into their particular configuration from their natural structure of substitution patterns on that. But that can vary. And that varies because when we revert this reaction backwards, we form a carbonyl here, and that oxygen could come in and attack either from above or below, forcing the OH, our carbonyl oxygen, into different locations. Okay? Why does that matter? Well, what's the difference between the green oxygen and the blue oxygen? One is axial and one is equatorial. Why do I care about that? Why did we study axial and equatorial? Changes the energy of the overall structure. An equatorial OH is more stable than an axial OH. And if we think about your reference to glucose, because it's Anthony's fault, of course. Okay, you're welcome.
Because I'm fat.
No, because you said glucose was used for energy.
Oh, that's what you're talking about. I thought about because I just have
Which one would we expect for our energy? The blue OH or the green OH?
the blue
Why the blue?
because it's higher energy.
And if it's higher in energy, that means it's more
reactive.
reactive. So if we're talking about energy, I want to be able to get access to it. I need a high energy form. The green form happens to be
Less energy.
low in energy. We don't run our fat stores, it's not technically fat, but our glucose stores, okay, with the low energy form. Because it's low energy, it's not easy to react. It's very stable. Does that mean if we look at glucose, we only see this blue form?
No.
No, we also see the green form. The blue form is used for energy storage. What's the green form used for?
Energy being, that's about to be used,
Nope. If it's used, I'm trying to pull in the blue form. I need to be able to react it.
it would be stored.
It would be something that doesn't react.
Oh.
Where could I use glucose where it doesn't react? It's a fun little molecule called cellulose. Guess what makes up cellulose? Glucose. You mean the same molecule that we use for energy and we process so that we can live and take apart and build things and all that? Okay. Plants use to build structures. Do you want your structure to be high energy so that it falls apart all the time? No, that would be a horrendous idea. So what happened?
Made it low energy.
They use the low energy conformation of glucose. That low energy is now not easily processed, and it can be used for structure. And so you get two forms. Those two forms, I believe, though I can't guarantee it, are known as alpha and beta. Not because we're talking about the alpha position or the beta position, because they're attached to the exact same spot. It's alpha and beta because they discovered one before the other. Why would they discover alpha before beta?
Because the alpha is the less,
Flip it.
is the more reactive one.
It's the more reactive one. If we're trying to study how things function, we're going to look for the things, we're going to find the things that are more reactive first. And so I would bet the alpha form was discovered because it was high energy, very reactive. And the beta form was found second. And they went, oh crap, we've got two forms of glucose. We need to call them glucose 1 and glucose 2. 1 and 2 sounds stupid. Let's call it alpha and beta, because everybody likes the Greek alphabet. Hooray, David.
Especially science and math nerds really like.
In any case, we're done.